So this is unit 3, lesson 5, first part on vectors. So we're going to go through this quickly. So firstly, what is a vector? You have to note this in your notebook, right? Vector is a quantity that has a direction and a magnitude. And what I mean by a magnitude is some kind of measurable quantity to it. Okay, it could be speed, distance, time, all these different things. So an everyday example of a vector would be, if you check the weather, it will often tell you the wind by showing an arrow. In this case here, say for example, it tells you that the wind is traveling at 30 kilometers per hour and it's traveling to the southeast. So there's two aspects of that vector. There's its direction and its magnitude being, in this case, its speed. So what we tried to do is, we tried to classify all that with numbers. So for example, what we would have here, notes in this notes on vectors section. Every vector has an initial point, which is the point where it starts, and a terminal point, which is the point where it ends, which has the arrowhead on it. So for us, when we're trying to represent a vector, the size, the length of the arrow should kind of be an indication of whether it's a large or small vector. So for example, if you're talking about a wind blowing to the northwest, like that, or sorry, to the northeast, that would be relatively small. This one here is bigger, which would mean that the wind strength is greater. So, and you'll see at the bottom of the worksheet, I just have some little notes for you to take on it and how it works. So we're going to look at some problems on that now. So we're going to see now how we write vectors in component form, and it's not that terribly difficult, but it just takes a little bit of practice to get used to it. So when we want to write vectors in component form, what we do is we start from its initial point, which I've just dotted in green, and we see, okay, if I want to get across to the terminal point, how far to the horizontally do I have to go? So if I look, starting from that terminal point, it's 1, 2, 3, 4 units to the right. And then I have to go 2 units up. So we would say that that vector is the vector 4, 2, or that's its component form, is 4, 2. Look at B. If we start from the initial point, well, we don't have to go left or right. So that means that its horizontal component is 0, but we have to go down 3, which means minus 3 is the vertical component. And finally, vector C, starting from the initial point, it's 3 units left and 4 units down, so minus 3, minus 4. Okay, so the next part, we say that two vectors are equal if they have the same component form. They might not start from the exact same place, but they have to be going in the exact same direction and with the same speed. Okay, so if you have the same component form, those two characteristics will be satisfied. So it's asking us here to write the coordinates of the initial and terminal points of two pairs of equal vectors. So it wants you to write two vectors that are equal and two more vectors that are equal. So let's just say, for example, we want to write two vectors that are 2, 3, or that have component form 2, 3. Okay, so we'd say the vector A, well, it could start at 0, 0 and end at 2, 3. Okay, so that A has initial point at 0, 0, terminal point at 2, 3, which means its component form will be 2, 3. And that means that that vector satisfies that condition. Now, what about a vector B that starts at, say, let me clear that, 2, 2. Okay, so if we want its component form to be 2, 3, it starts at the point 2, 2. Where should it end? Well, it should go 2 units horizontally, and it should go 3 units vertically, and there you go. Now we're moving through this pretty quickly, so the next thing is the magnitude of a vector. The magnitude of a vector is basically the length of the arrow. So what you can do is you can apply the distance formula to it, which is something we should know, or we can just write out its components and use Pythagoras' theorem. So if we look, the first vector starts at 5 and goes to minus 6. So its horizontal component is minus 11. Okay? And its vertical component is minus 3. Well, it's actually positive 3. So it goes from minus 2. So I'm going to just rewrite that just to get that in better. So horizontally, it goes from 5 to minus 6, which is minus 11. And then it rises 3 units here. So look, you see the way I'm drawing it to represent the fact that one vector is bigger than the other. So it's a right triangle. So you can use Pythagoras' theorem. So we'd say that this is the vector AB, and this is how we write it often, AB with an arrow over it. So we have minus 11 squared plus 3 squared equals AB squared. And if you use Pythagoras' theorem correctly, you'll find that the vector AB has magnitude, and we put these absolute value bars on it to say that we're talking about the size of the vector, and it's going to work out to be the square root of 130. All right, so you can have a look. Look, there's a second question for you to practice. And also there's a couple more here on this slide, but if you see, right, with this slide here, what's important here, it's telling you, you don't have the initial and terminal points here. You actually know how far it travels horizontally and how far it travels vertically. So you actually know what numbers to fit into Pythagoras' theorem to do it. So adding two vectors, right, I'm going to do this one quite large. So if you just read what it says here first, it says, to add two vectors, you put the initial point of the second vector to the terminal point of the first vector, and then you draw a segment connecting the initial point of the first to the terminal of the second. Okay, when I'm reading it out, it sounds more complicated than it actually is, but here's how it goes. So if you look here, the first vector is 3, 4. It doesn't matter where you start. Okay, so the initial point can be wherever you want, but what's important is that we go 3 units to the right and 4 units up to get to the terminal point. So I'm going to start here, okay, where I put the blue dot. So I have to go 1, 2, 3 units across, 1, 2, 3, 4 units up. Okay, and there's my first vector. Now what's important is the second vector starts from where that one stopped. So my second vector has to start here. It goes 2 units horizontally, 1 unit vertically, and it ends up here. Okay, and now to finish it, you connect the start of the first vector to the end of the last vector, and it goes there. So now if you want to write your resultant vector in component form, you'll see that we start from here, we go 1, 2, 3, 4, 5. So that means our horizontal component is 5. And it rises 1, 2, 3, 4, 5. So our vertical component is 5. And if you look, you get that from adding the components of the first two vectors. So this is a visual demonstration. You may be asked to do the visual side of it, but if not, you can just add the components. Okay? So there's a couple more practice examples there for you to do on the next slide. But they're pretty easy. So demonstrate it, and also write the component form and check that it works, that you just add the components. And lastly, the last thing I want to show you here is subtracting two vectors. Now this is easy, but it doesn't come up very often, but I still want us to know how to do it. So if you look here, you will see that the vector S, if we write it in component form, is from the initial point we go 3 left and 3 down. So it's minus 3, minus 3. And the vector T is 3 units to the right, so 3, and 2 units down, minus 2. So if we want to add those, or if we want to subtract those vectors, what we do is, we take the first one, and what we do is we add the negative of the second vector. Okay? So it's like we add minus t. So instead of doing plus 3 minus 2, we do plus minus 3 plus 2. And that will give us then that when you subtract those two vectors, you end up with the vector minus 6, minus 1. Okay? So that's the basics on vectors. That's where we should be on vectors at this point.